So today's topic is quantum computing, which I think is very, and post-quantum encryption, which I think is very interesting. And I got another project running on it today because just about a week or two ago, they approved a second quantum encryption algorithm, and now we got them both in the projects. So let's start with that. Chapter 14 is here. There. And I turned on a quiz for this chapter, which is extra credit. You don't have to do it, but it's an option in Canvas if you feel like taking a quiz on this topic. And the projects are also extra credit because this is, but it's probably important to learn this stuff. All right, as this is where we're all going to have to move to. Anyway, so we'll talk about how quantum computers work. And my goodness, a lot of typos on this page. Anyway, all right, so quantum computers. This is a real important issue. Now, if you may not remember, well, if you ever learned this at all, I learned this maybe 50 years ago, how normal computers work. Because I came in when transistors were still done one by one, really before modern computers. And so you would have a NOT gate where you put a voltage signal in and it puts the opposite signal out. So if you feed in a high voltage, out comes a low voltage. If you feed in a low voltage, a high voltage comes out. That's 0 and 1. So the A and Q. Then you can have AND gate, where there's two inputs, and they both have to be 1 for the output to be 1. If either one of them is 0, the output is 0. And then you have an XOR, where you feed in two signals, and if they're different, the output is 1. But if they're the same, the output is 0. So these are the basic operations from digital computing. And just by combining these together, you make a digital processor. With millions of these on a chip, that's basically what the Intel processor and the AMD processor are. They're just performing these simple elemental operations on bits. And the bits are always 0 or 1, and they're combined in one of these ways to create new bits that are just 0 or 1. And so you can combine them and make an adder this way by combining a series of these things together, and so on. You can build all these circuits with just a lot of those fundamental components. All right, now real devices are analog. The actual voltage, if you measure it on a chip or in an audio waveform or anything, it's going to vary like this. And so what you do is you digitize it. You say anything above a certain threshold, you're going to call a 1. Anything close enough to 0, you're going to call a 0. And that's how you do it. And you try to minimize the time it spends in the forbidden zone in between. And therefore, there's a possibility when you store or recover information or when you transmit information that it will be lost, because noise could cause an area that should be 1 to be misunderstood as 0. And therefore, you need error correction to fix that, so you don't just transmit data and trust that it got there. You transmit data, and then you add something like a hash value or a checksum, so you can calculate that at the other end and make sure the data got sent correctly. And if it didn't, then you retransmit it. That's how Ethernet works, and a lot of other protocols. All right, so there was analog computing back in the old days. This is the relic of a thing from BC that was an early analog computer to simulate the motion of the planets in the sky so you could predict their future position for things like weather prediction and astrology. And a slide rule is another analog computer where you have these marks that are spaced out in a logarithmic way, so you can do multiplication by sliding these sticks and adding numbers together on a log scale, which turns into multiplication. You can do multiplication and division on an analog way with these devices. So, all right, now consider a flute. If you play a flute, you blow in one hole here, and you put in what's essentially white noise. And the structure of the flute is such that certain frequencies resonate and are amplified. Other frequencies don't resonate and are canceled out, so you get a pure note coming out of this, even though you put in white noise. You can regard this as an analog computer. It took a signal that contained many frequencies, and it isolated certain frequencies and let them out and got rid of the other frequencies. And now you can ask, how many bits does this process? And you really can't answer that question. You started with an analog white noise signal. You got an analog frequency output. You could say something about the spectrum content of the white noise and something about the precision with which it gives the frequency you want out here, but it isn't as simple as saying it has bits. It's not digital. It doesn't work from bits. And I bring this up because it's a fine example of an analog computer. This is a thing that does some kind of processing on input information to create output that you want, but it does not do it digitally. It does it in analog form And that's what quantum computers do. In quantum computers, instead of having bits that are 0 or 1, you have qubits. And qubits live on what's called the Bloch sphere. They have all these, there is a value that is 1 down here, and there's a value that's 0 up here, but there's a whole bunch of in-between states called superposition states, where it is in an uncertain state that when measured will sometimes be 0 and sometimes be 1. But this is a real state before measurement, and it's a superposition state of both 0 and 1. And this means that a single qubit contains a lot more information than a bit. It's an analog object that includes a lot of information. All right, so 1 byte has 8 bits of information in digital computing, 256 possible states. But if you have 8 qubits, then you have 8 numbers, and each one of them has basically two angles, phi and theta, 2 analog values. So each one of those 8 qubits contains a whole range of possible values, far more information than 1 bit. So it would take 256 complex numbers. Well, I think not that much. I think it would only take 16 complex numbers. But anyway, it'll take a lot of numbers to specify the state, phi and theta for each of these. It's a lot more value. So there's a range of states. So in digital computing, n bits have n bits of information. In qubits, it contains 2 to the n complex floating point values. That's one way people explain it. Anyway, it has a whole lot of extra information. Now, the issue, of course, is how precise is the qubit, and that will have to do with the noise level of the hardware, and that's what limits current qubits. Anyway, so now you can make a quantum algorithm. You feed in some qubits, then you have a circuit of quantum gates, and then you subject it to measurement, and then you get some kind of output. And so by designing your circuit correctly, you can do computation this way. So you have these quantum gates are what the analog of these things back here that did logic gates, not AND and XOR. These are the fundamental logic gates that run digital computing, and these are the fundamental quantum gates that run quantum computing. So here's measurement. That's where it stops being uncertain and is forced to settle down to either 0 or 1. Then there's a 180-degree rotation about this x-axis, which would change a 0 to a 1, or it would change one of these uncertain states to a different uncertain state. And then there's a Hadamard gate, which is a 180-degree rotation about the xz axis, which would change a 1 to a minus 1. I'm not quite sure what this xz axis is, about y. I'm having trouble explaining it in the diagram, but anyway, this converts a certain state to a superposition state. All right, and I guess it's about this diagonal. So I'm trying to imagine it. So if I started at 0 and then rotated about that diagonal 180 degrees, I think I would end up pointing, I can't quite envision where it goes. But anyway, we'll see it when we get to the hands-on part in Python. We can do it and see what it does. As far as visualizing it here, I'm having a hard time doing that. Anyway, then that's why you have the quantum speedup. I mean, for example, consider searching an unordered list of n items. If they are not sorted, then there's nothing faster than just looking at every item one by one to see if it's the one you want. So you'll have to look through all of them, and if you're going to find it, it'll take, on average, looking through half of them to find it. So something like n over 2 operations is what you'd expect to do. And a quantum computer, turns out you can do it in square root of n operation using something called Grover's algorithm. And there are quite a few operations that are sped up like this. They get much faster on quantum computers. Simon's problem is a little bit like hash collisions. So you're finding a function where two different inputs will lead to the same output. And it turns out in a classical computer, it takes 2 to the n over 2 operations, which we've talked about before. If you have an MD5 hash with 128 bits, you'll have to do 2 to the 64 calculations to find a collision. In a quantum computer, it's much less. You just have to do n, like 64 operations. So that problem can speed up quite a lot. And this is the circuit that does Simon's problem efficiently. You feed in a bunch of qubits, you go into a complicated structure here with the gates, and out comes the answer. So Shor's algorithm is the most important one and the one we talk about most because this is the one that breaks RSA. This will factor composite numbers into their prime factors. And if you could do that efficiently, that would break RSA. And that, in general, it can solve the discrete logarithm problem and the elliptic curve problem. It can break all of our modern public key encryption schemes, which are all mathematically related. And here's what it looks like. It's a whole series of gates. These are X gates. These are entanglement connections between them. And out here is the measurement. So this pattern of X gates and then entanglement operations and then measurement, you can feed in an encoded version of a composite number here, and you will get information about one of the prime factors out here. And it just propagates through this network, and in principle, it does work. In practice, I think the only thing they've ever done is factor 15 into 3 times 5. At least a few years ago, that was the only one that actually been able to do on modern hardware. But in principle, if you had enough qubits and they were low noise enough, you could break RSA, real RSA keys, like 1024 and 2048-bit keys with this thing. And that's what everyone's worried about. So now AES is not that bad. It turns out that you crack private key encryption, like AES, on a classical computer, it would take something like 2 to the 128 calculations to break in. You could say maybe half as many if you want to say you're going to go till you have 50% chance of finding the key. In Grover's algorithm, it turns out to take the square root of that, 2 to the 64 calculations. So that is not such a big speed up. Now, it's a big speed up. It means that the 128-bit security of AES is down to 64 bits, which, as you know, is not really good enough anymore. 2 to the 64 is not an impossible thing for an attacker with a lot of resources, but what you can do is just go to 256-bit AES that already exists, and then it would still take 2 to the 128 calculations even on a quantum computer, and that's still impossible. So we don't need to replace the private key systems with new private key systems for quantum computers. All we have to do is switch from AES 128 up to AES 256, and we'll be okay. So that's good news. AES does not have to go away. All right, and so anyway, like I say, double the key length and it'll be secure again. So now the problem is, like I mentioned, current hardware cannot accomplish any of these miracles, not even close. It can only do pathetic things like factor 3 times 5, and that's because of noise. The problem is the qubits are formed from superconducting circuits cooled to extremely low temperatures, and they're only stable for a few milliseconds. That's one form, so that just the remaining thermal motion is enough to cause noise, which is enough to greatly disrupt the computation. Another technique uses ion traps in crystals. There's a bunch of different atomic structures that have quantum properties that could in principle be used for quantum computing, but you need to be able to build not only the qubits, but you need to be able to build all these gates. So you need to have some way to build an X gate and some way to build an H gate and to do a controlled measurement. So it's quite a bit of effort. You have to have some kind of substance to build the qubit out of, where you can also build all these other things. And you have to figure out some way to transmit qubit information from one location to another, like a networking cable, and some way to store it, like memory. And all those have been done, but all of them are very complicated and difficult and just in early hardware prototypes that don't work very well. So the current quantum computers are just a proof of concept, and they don't work all that well. But there's a lot of companies out there like IonQ, they claim they have the most powerful quantum computer and so on. A bunch of people every month or so, there's another huge advance forward in quantum computing. So everybody thinks this stuff is really coming, and maybe in 20 or 30 years, it'll really be here and really solving problems like breaking RSA. So we have to move to new encryption schemes now, because it's likely that our current encryption is going to fail in a couple of decades, so we should plan ahead. So you need to have a different hard problem. Remember, all encryption requires a hard problem. You want breaking in without the key to be the hard problem. And so you can't use the discrete logarithm problem anymore, which is what all the current systems use. So there's 4 types: code-based, lattice-based, multivariate, and hash-based are the 4 types of hard problems that cannot be broken by quantum computers. So code-based is based on error-correcting code. The first one is Michaelis, and this, by the way, is the new one that's just approved last week. It'll be in the projects coming up. And you can do encryption and signatures with it. And here, at this time, the public key is 100 kilobytes in size, but we're going to see it's in fact now down to just about 2 kilobytes in size. So it's gotten better. All right, so what you do is you want to send a 3-bit message like 010 over a noisy channel. So one thing you could do is send every bit 3 times. And if a single bit was wrong, you'd be able to tell. But if 2 errors occur, then you might still get the wrong answer at the other end. So that's not a great idea. So another way to do it is that's linear codes. Let me see, is it more of the same system or the next one? Okay, it's still more of the same system. So the next thing you can do is have a code where you treat it as a vector, multiply it by matrix G to form a code word. This can correct multi-bit errors. You're sending more total bits, but the total bits have repetitive, redundant information, so you can correct even for multi-bit errors. And here's McLeese encryption. You make a combination of 3 matrices, and then you encrypt your signal by multiplying your plain text by this and adding an error bit. And the private keys are A, B, and C. G is the public key. So anybody can encrypt data. They take their secret message, they multiply it by this G matrix that is public, and they add a random error bits to it, some random errors to it. And then that creates an encrypted message, but the only person that can decrypt is the person that knows A, B, and C. So logically, it's the same as RSA, right? There's a private key. People that have the public key can encrypt your data, and only the person who holds the private key can open it. It's just that the mathematics underlying it is this recovering data from a signal with error problem, which they call code-based. All right. So that's one way to do it. It relies on the hardness of decoding a linear code with insufficient information. This is known to be NP-complete and beyond the reach of quantum computers. There is no quantum computing algorithm that anyone has found that makes this faster. So this will be a good way to encrypt data, and even quantum computers will not crack it. And it just has been approved, like I say, a couple weeks ago by the National Institute of Standards. This is the other one that was improved a couple years ago, is a lattice-based scheme. So a lattice is a series of points with a periodic structure. So here you've got a row of dots and a row of dots halfway in between the next row, sort of like the way atoms are lined up in a salt crystal or something. Okay, and so now you can consider various vectors here. V and W are basis vectors, if you like. You can pick 2 vectors, like this, and then you can construct this whole lattice with just those points by adding multiples of V and multiples of W, including negative, going the other direction. You can find a path from a starting point to all these other points. So if you just make the set of all the places you can get by adding integer times V plus another integer times W, you'll create the lattice. All right, so here's a problem. Combine basis vectors to find the lattice point closest to a point. So I have a point here, and I want to figure out how to find that point. What combination of these vectors does it need to get to the point closest to that point? Now, in a simple case like this, you could probably figure it out, but in a complicated case with many more dimensions and many more dots, this turns out to be a hard problem. So that's the game, and so here's a way to do it with mathematics. A is a random matrix, Q is a prime number, and B is a vector. And so you're trying to find a secret vector so that a random matrix times the secret vector will take you to the vector you're looking for. This is another way to look at it. I think this is more explanation of the same one. Let me just go back and make sure. Yeah, the multivariate is, okay, good. All right. So this is the diagram that's easy to understand. It's easy to understand the problem here. That's what the hard problem is. All right. And so, okay. Then there's learning with errors. And this is where you have A and B, find a secret vector so that A, S plus E mod Q is B. And so E is a random vector of noise, and you're finding a secret vector here again. This is another expression of the problem. All right, so I see these 3 problems are somewhat equivalent, and they're believed to be hard for both classical and quantum computer. So that's the game. This one here is the one that is Kyber. Kyber, that we're going to do a little bit later, is the approved NIST standard encryption based on this lattice problem. All right. And then there's the multivariate problem where you have 4 unknowns and 4 equations, but the equations are quadratic. Now, if they were linear, it would be easy to solve with standard algebraic methods, but since they're quadratic, you have things like x2, x3, and x1, x4, and so this can be very difficult to solve. And so the actual hardness depends on the parameters. It's hard to choose secure parameters. Various schemes have been broken. So this is starting to sound like the RSA, that video I played last time, where they say, RSA in practice is not very good because there's a bunch of subtle mathematical problems where it fails. And this multivariate system is sounding like the same kind of rat's nest. And in fact, no multivariate system has been approved yet by NIST. So nobody has, in fact, found a way that was considered good enough to do this. But, so people are worried about it. It has short signatures, but it could be done. There's also one using hashing based on a difficulty of finding hash collisions, and those are complex, and something called the Winternitz one-time signature is another way to do it. Signatures can be forged, however, in this system. And like I say, nobody's using it yet. This method has not been approved by NIST. The other methods are the ones that actually survived the multi-year vetting process to come up with a system that's actually practical, and they recommend it thinking it's going to be trustworthy. So anyway, it only works for short messages, and it only works once. If you use a private key twice, then you can forge other messages, and there's no simple way to fix this problem. So it doesn't sound that great, neither does the multivariate one. They have problems, and maybe those problems are why they haven't been approved yet. I haven't gone into the math in enough depth to know why. Anyway, the state-of-the-art schemes use more complex versions of it with tree data structures, like Sphinx, with signatures that are dozens of kilobytes long. So people have developed systems based on this, but they have not been approved. All right. So how can things go wrong? One thing about security proofs, as we've seen all through this course, is it's hard to prove exactly how secure your system is. Typically, your proof only just applies to large values of the parameter. In practice, you use smaller values, and it's difficult to quantify exactly what level of security you have. And new schemes, like these post-quantum schemes, unfortunately, because they're new, people don't really know how many ways there are to attack them. It's certainly far more likely that within a few years somebody will find a new attack that breaks them than it is if you use the older scheme like RSA. So that's why none of them are, that the security levels are not formally approved yet of post-quantum schemes, because realistically you're going to have to wait more years before we have more trust in them. All right, and so that's the question. Post-quantum encryption is more important than post-quantum signatures, because if signatures are broken, that doesn't really expose private data. All right. And in Diffie-Hellman often uses more than the shared secret to form the session key, so that would make it safer against quantum computers. So that may provide some comfort to people using the old systems. And of course, implementation issues pop up. Some post-quantum encryptions have been optimized and are therefore vulnerable to timing attacks. We talked about this before. The most efficient code takes shortcuts. If it's about to multiply by 0, it doesn't bother. It moves on to the next term. But if you do that, then the time it takes gives you a clue about how many zeros there are in the private key and things like that. So just like I said, the post-quantum algorithms are going to be more risky in that somebody is more likely to develop an acute mathematical trick. They're also more likely to have defective software at first, because the software just hasn't been through so many generations of improvement. So here's some standards. In 2022, Crystal's Kyber was approved. That's the lattice-based encryption scheme that's approved. And HQC is the one that was just approved in March, last month. Hamming quasi-cyclic. And that's based on the code-based scheme. And then there are some digital signature algorithms, Crystal's dilithium, Falcons, and Sphinx Plus that we mentioned are approved. So one of those systems that I said was pretty complicated was in fact approved for digital signature, the hash-based one, I think, but not yet for encryption. All right, and so Kyber looks like this. You have these matrices of polynomials. And so your private key is just a polynomial of small parameters like this, x cubed, x squared, and x, and then another term, x cubed minus x, a vector with two polynomials. The public key is A and T. And A is a matrix of polynomials, and T is a vector of polynomials. So like I say, you have to be a little bit comfortable with vector and with algebra and vector calculations to do this. But anyway, I'll demonstrate these projects. We can do it. And the Hamming quasi-cyclic one uses structured lattice. Kyber uses lattices. This one uses error-correcting codes. It's a lengthier algorithm demanding more computing resources, so this is not recommended by National Institute of Standards as the most common algorithm to use. It's a backup choice in case Kyber fails. And as I've said, there's a pretty high chance that these post-quantum algorithms will fail because they're new and a lot of mathematicians have not yet spent a lot of time cracking them. So the HQC algorithm has various levels, 128, 192, and 256, and those have claimed security levels and longer public keys. But like I say, the smallest security, which is roughly like AES 128, has only about 2,000 bytes for the keys, which is not too unreasonable, considering that an RSA key now is 2,048 bits. Now it's supposed to be going up to 4,096 bits. It's not much bigger than an RSA key, which is nice. All right, so let's try Kahoot, which is 12 here. Enough competitors. But, all right, we'll carry ahead anyway. The people can see the questions. All right. What? Oh, this is the wrong one. Never mind. Maybe I don't have one for chapter 14. Chapter 12 is ECC. I may not have one for chapter 14. Well, never mind. I'll just stop then. Wait, I do have one. There we are. I thought I had one. There, good. All right. But you'll have to log in again. Okay, let's try it again. This is the right one. All right. You made it. I'll wait till the end of the song to see if anybody else is coming, but we may have only one player today. All right, so what term indicates a qubit that might be 0 or 1? All right, that is a superposition state, a mixture of 0 and 1. That's what it's called. Entanglement is when you connect two qubits together, so they're forced to have the same state. All right. So which attack can break AES 128? It was Grover's attack that does it, all right? That makes AES 128 solvable in 2 to the 64 calculations, which is not an impossible task, assuming we have much better quantum hardware than exists yet. All right, which system is based on the closest vector problem? That's the lattice-based system, all right? Like Kyber. All right, which is a component that performs computation on qubits? I call those things gates, the things that perform operations, things like H gates and X gates. All right. And in digital computing, you call them logic gates. All right, what attack can make AES 256 unsafe? None of them. AES 256 is fine. None of these attacks can break it. We don't need to replace it. All the attack will do is lower the complexity down to 2 to the 128 operations, and that's still impossible. So this is a fine system. Quantum computers are not a threat to it. All right, and what does McLeish encryption use? It's code-based. All right. So, IDK is one, I know. And the other is base. I don't know who they are. You'll have to tell me who you are if you want your points. I think IDK told me who they were last time. All right. Let me stop this video.